Good afternoon everyone and welcome to our second session on analog mixed signal design. I hope all of us are connected now, and we will begin with where we left yesterday. Yesterday we went through detailed discussion on MOSFET as a device. We looked into the DC characteristics, we looked into the small signal analysis, small signal model, how does the small signal parameters come into picture, how do they make physical sense, what is their dependencies on device parameters or the sizing parameter that we have in hand as designers. We also looked into the high frequency model, that is related to the frequency response of these devices. We understood the concepts of parasitic capacitances, what is their origin and how they play a very important role in determining the performance of the circuits. Following that, we looked into another very important concept, that is noise, and we incorporated all these four analysis: DC analysis, small signal analysis, high frequency analysis and noise analysis into analyzing a simple common source amplifier with resistive load. We also looked into a few issues related to design optimizations, just a small example where we are trying to maximize or increase the small signal gain by tweaking some of the parameters like RD or the ID while maintaining some other parameters like the signal swing and the bandwidth, and we got a taste that okay, what kind of design conflicts we are going to face when we look for practical circuit design issues, when we are trying to meet certain specs in terms of power, in terms of gain, bandwidth, noise, swing and so on. We see that there are so many different parameters coming together and so many different specs coming together, and that is the beauty of analog design. We need to come up with a holistic solution close to the best feasible solutions using our understanding and knowledge of the circuit operation and how does it depend upon the device parameters and how does it link to the high level specs. So, continuing from where we left, we will be looking into common source amplifier with active load. Yesterday we did it with resistive load, we are going to do it now with active load, and that is going to be linked with our discussion on front end, because in the front end we will be using differential amplifiers, two stage amplifier in form of op amp, and ultimately whatever analysis is required for those amplifiers boils down to common source amplifier with active load. So, whatever we will be doing today, it is ultimately going to be linked directly with our front end amplifier design. Once again, starting with DC operating point, small signal analysis, frequency response and noise analysis. Along with that, the peripheral circuit like current, mirror, we are going to look into design of these, and all these four analyses are going to be applied to the common source amplifier with active load. And once we are done with this process, we will be ready to go into differential amplifier and multi-stage amplifier, which is going to be the building block for our low noise front end amplifier for the analog front end. So, let us start our discussion on common source amplifier with active load. So, yesterday we have discussed a common source amplifier with resistive load, where we took a simple example, capital VG is the DC voltage, on the top of that we are applying a small signal VG and we are looking at the small signal VD produced, and we noticed some techniques through which we can improve the gain. So, one of the possibility was increasing RD, and we mentioned that when you are trying to increase RD, it directly couples with the VD. So, if you are trying to increase RD, the DC voltage VD is going to come down, and as a result you are not going to get the maximum possible swing that we want. So, signal swing is directly related to the RD. Larger RD means lower DC point for a given current, and as a result the gain over here can trade off directly with the signal swing. So, this is one of the disadvantage of using passive load. Another issue is the area of these passive element that is to be implemented on an integrated circuit. So, when you are talking about integrated circuit, passive resistors can be implemented in several ways, and in general they take good amount of area as compared to the active devices, the MOSFETs. The area consumed by these passive resistors, capacitors can be pretty large, and as a result we can if you can avoid the use of these passive elements and use active loads, that is employing CMOS transistors, either PMOS or NMOS directly as load elements, probably that can be advantageous. So, that is the main motivation behind using active load in presence in place of this passive component RD. So, let us talk about an ideal active load, which is a current source. So, what happens to the circuit if I replace this RD with an ideal DC current source ID and then do the same analysis. So, what is the property of an ideal DC current source? This must remain constant. Therefore, there is no ID, small signal ID is 0. This current flowing into the drain will never change. So, how does this give us any gain? So, if we now look at our current equation of the MOSFET, I have ID in saturation region. So, we have these two terms combined together, these two terms should remain, the product of these two terms should remain constant. And now, if we are trying to increase VGS, that means you are trying to increase the first term VGS plus small VGS, that means in order to counter this, the second term must reduce, you must have VDS, if I call it a positive quantity. So, VDS is a positive quantity. So, taken together the second term should reduce if I am increasing the first term. So, that the product remains constant. And now, if you see the dependency in saturation region, this lambda is very small, right. So, maybe for 180 nanometer maybe 0.01, 0.02, and therefore, in order to counter this small change in VGS, which is having quadratic dependence, I may need a very large change in VDS to balance this increase. So, the increase in the first term has to be balanced by the reduction in the second term, and in order to counter this increase arising from this quadratic term, I must have pretty large reduction in the VDS, that is this small VDS must be large, because this is getting multiplied by lambda and then resulting in the overall term. So, that mandates large reduction in VDS to have compensation for the first term, so that the product remains constant. So, that is the basic mechanism for obtaining gain in this circuit. So, when we are trying to reduce VGS, same thing will happen, this first term is reducing, I need a large increase in VDS, so that the increase in the first term is compensating the reduction in the second term. So, here if we want to do the small signal analysis, this is a DC current source. So, how does the small signal model look like? So, once again Vg is set to 0, capital Vg, we are only going to deal with the small signal Vg. You have Gm VGS. The current source is ideal DC current source, there is no small signal current flowing into this, and we know that for ideal current sources, ideal DC current sources, we open circuit them in small signal analysis, because there is no small signal current flow. If there is no current flow in any branch, that means that branch can be open circuited. So, since there is no small signal current flow in this branch, I can open circuit this in my analysis, and therefore, the drain terminal, we disconnect the DC current source, and we know that RO is just going to come between the drain and the source. Source is grounded and we have the G. So, here we get an overall gain because of the applied Vg. Gm VGS flows into RO. Now, remember that when we say that Gm VGS flows into RO, we should remember that it is not that we have a physical RO existing in parallel with the NMOS. It is just the physical characteristics of the device which is giving rise to this RO, and the basic mechanism is over here. So, this is just a compact mathematical representation of what is happening physically using this equation. So, we should always have this in mind that this is a small signal equivalent parameter which is capturing the large signal behavior, which is capturing the effect of this large signal equation when we are applying a small signal. So, this RO is of course not a physically existing quantity, it is just capturing the behavior of the MOSFET. So, in this case we say that this Gm VGS flows into RO, and therefore, Vd is going to be equal to minus Gm VGS times RO. Therefore, the gain is minus Gm RO, which is Vd upon Vg. This is called the intrinsic gain of the MOSFET. So, if you are having an ideal current source connected in the drain, we get maximum possible gain of out of this common source amplifier, which is equal to minus GMRO. So, once again we can look at what is going to happen to this small signal gain if we are trying to play with these parameters. So, if you are trying to increase the gain, what are the options that I have? So, suppose I increase my ID, what do we expect? So, we know that if I am increasing my ID, GM is going to go up by root ID, but RO is dependent upon 1 upon lambda ID. So, my gain will go up if I am increasing my ID, the gain will go down by a factor of root k. Suppose I increase the ID by k times, the gain will go down by root k. If I am reducing my ID by k times, the gain will go up by root k. So, now how do we implement this ideal current source, or at least a current source which is close to this ideal current source in our actual circuits, so that we can achieve this kind of relatively large gain in our circuit. Before we proceed that, one of the important points that we would like to emphasize here, in case of passive load, we knew what is the DC operating point at the drain. This is Vd, where Vd is equal to Vdd minus Id Rd. So, we have a very well defined DC operating point at drain. So, remember, in order to have a well defined DC operating point, we need a well defined DC at the gate, well defined DC at the drain, and hence a well defined ID DC current. So, the drain voltage, gate voltage and the ID should be well defined, and on the top of that we can superimpose some small signal to get my amplification. And a well defined DC operating point ensures that for the entire range of the input signal, my transistor is going to remain in saturation. That is the purpose. So, here what can we say about the gate voltage? Okay, once again we do have the facility or freedom to choose Vg. We are using a current source. Suppose you have a current source available with you. So, again we have the facility of providing this ID, but what about Vd? So, here what is the equation of Vd that I can write if it is an ideal current source? So, one of the ways is to solve this equation for a particular lambda, right. So, here if I just solve this equation considering the effect of lambda, Vgs minus Vt square is known to me, Id is known because this is fixed by this ideal current source. So, basically the Vds from this equation, if I want to find out, this will be Id upon this constant factor, which is 1 upon 2 mu n Cox W by L Vgs minus Vt square minus 1 upon lambda. So, that is the value of Vd that I expect. So, remember here what we are saying is Vgs is being fixed, we have the freedom to choose Vgs, we have used a current source, ideal current source. So, we have chosen Id. Therefore, this gives us that the Vd is dependent upon this lambda, 1 upon lambda, and in general lambda is not a very well defined, very precisely defined quantity. It can vary a lot from device to device on a single chip, and as a result this is not a very well defined Vd. Vd as a result can vary a lot. Some device can have lambda of 0.01, some other device can have a lambda of 0.03. So, Vd can have 100 to 200% variation, and as a result we are not sure whether the transistor over here is going to be in saturation region. So, it seems like we do have a problem with respect to DC biasing. How do we set the DC operating point of this MOSFET? That is the problem with active load. So, it seems like yes, gain point of view we can get a large gain minus GMRO, but from the point of view of DC operating point we are having a problem. So, we are going to see how can this problem be addressed. So, let us first talk about quickly how to implement this ID. So, once again in general on an integrated circuit if you are talking about an analog IC, we may have a certain mechanism of producing a relatively precise, stable current source, which is going to be independent of supply, independent of VDD. So, there are mechanisms through which I can produce an IREF, a reference current, which is independent of VDD. So, if time permits, we will go through some basic techniques through which we can generate a well defined reference current, which is quite controllable. And using this reference current, I can create current source, I can form a current source which is going to provide the bias current to my NMOS transistor. So, this is once again my earlier device. I have the capital Vg, on the top of that small Vg, and here I am trying to form a current mirror. So, this is a diode connected MOSFET. So, if I call this M1, M2 and M3, M3 is diode connected, drain and gate are shorted. Why do we call it diode connected? Because transistor is a 3 terminal device. Here we have shorted the 2 terminals, drain and gate. Now, it has become a 2 terminal device, it has become something like a diode. So, if you control the voltage at this point, the current is going to increase in a square law fashion. The curve may look like similar to a diode, and since the gate and drain are always shorted, it ensures that as long as the Vg is greater than Vt, the Vsg is greater than mod Vtp, in this case the transistor is going to be in saturation region. So, the first purpose is that it keeps the transistor in saturation region. Therefore, depending upon this IREF, I can find out what is the Vsg of this MOSFET. So, I can just write on the equation IREF is equal to 1 upon 2 mu p Cox W by L, call it W by L3. Vsg is VDD minus VGP 3 VGP 3 minus mod Vt p square. If I ignore the channel length modulation for this device, from this equation I can find out what is the VGP required to establish this IREF. If I do have to include the channel length modulation, I can do that. So, this will become 1 plus lambda VDD minus Vs, this is lambda Vsd. So, one thing Vsd is nothing else but Vgp. So, this will be again Vgp 3. So, in general, here we see that the Vd is equal to Vg, and therefore, the Vsd is not going to be that large. So, we can in general ignore this lambda while calculating the DC condition. So, from this equation I can find out what is the value of Vgp required, so that the M3 is having sufficient Vsg to support this IREF. So, the diode connected branch provides us a reference Vgp3, provides reference Vgp3. So, it is developing a reference voltage which is now applied to the gate of M2, and since this M3 and M2 they have the same source, same gate. So, once again for the M2, if I ignore channel length modulation, I can say the ID2 in M2, that is once again going to be 1 upon 2 mu n Cox W by L2, same equation VDD minus Vgp3, which are this is common, and Vtp square. If I assume that Vtp of these 2 transistors are almost similar, that means these 2 transistors are well matched, I can ensure that the current in M2 is going to be a copy of current in M3, because this term is constant, it is the same in both. And of course, you have the dependency on output voltage 1 plus lambda VDD, in this case it will be Vd, let me call this Vd. So, 1 plus lambda VDD minus Vd, because this is the Vsd for M2. So, as long as this lambda is small and VDD minus Vd is not too large, we can approximate this total current as just the first term, quadratic term, and therefore, it is just going to mirror the current in M3, mirroring ratio being given by the ratio of W by L for M2 and M3, right. Now, so one of the question is that why do we need the diode connection over here? Why can't we just do this? Is this going to work? Same thing, I am not connecting the drain and gate of M3. So, what is the problem here? So, in general, in integrated circuit or even in discrete MOSFETs, if you do not have a direct DC connection for any circuit node or high impedance circuit load like the gate, we say it is a floating node. In this case, this gate terminal of these two MOSFETs is a floating node. We do not know what is the DC voltage over here. And as a result, this can take any random value between VDD and ground depending upon some spurious current paths or the leakage current that is flowing through the MOSFET. So, there can be some leakage path. Ideally, the oxide should not conduct, but there is some leakage path. As a result, there can be some voltage, any voltage between VDD and ground can appear over here. We do not have a control on this voltage, and as a result, we do not have the control on VG. And therefore, if we are even ensuring that this is an ideal current source, a very good reference, IREF is a good reference and is remaining constant. So, what do we expect from the characteristics of M3? So, if I draw ID VDS of M3, these are different curves for VG1, VG2, VG3. So, this is how the ID VDS characteristics of a MOSFET looks like. So, if I am drawing these characteristics for M3 where my VG3 is not defined in a proper way. So, let me call this VSD because it is for PMOS. So, ID versus VSD. So, these are my VG3 is not very well defined. As a result, if I draw a straight line, my current is somewhere over here. So, if I draw a straight line, this is the IREF that I am putting in. For this IREF, I do not know where is going to be my VD. It can be here, it can be here, it can be here. I do not know where is my VSD. It is not well defined. So, since VG can take any value, it is floating node, it can take any value between 0 and VDD. As a result, if I look at this curve, the VSD can take widely different values. We do not have any control on the drain voltage at this node either, and therefore, this can be in triode region. We do not have any control on the operation of this transistor. Therefore, it is necessary to connect the drain and gate of M3, so that we make sure that the VG and the VD value are equal, and then we have a unique point in this plane. Once we make this diode connection, then we have a unique point, a unique curve only and a unique point only will satisfy this equation, because in that case the VD is equal to VG, we are forcing that condition. Then we do not have that undeterministic behavior. Now, another question that generally comes up: what happens if you have a diode connection for M3? Or rather M2, does the current mirror operation still remain? So, once again, if you look at the current mirror's behavior, we are trying to implement an ideal current source. The M2 is supposed to mimic the behavior of an ideal current source, which is copying IREF. And what is the property of an ideal current source? The small signal resistance should be very high, ideally infinite. That means, if the voltage at this node is changing, that means if the drain voltage of M2 is changing significantly while keeping M2 in saturation, the ID should not change much, it should remain constant. And that is going to happen when we are having the output characteristics such that the gate voltage is constant and we are observing the drain voltage. So, this is the curve when we have the gate voltage constant and then we are sweeping the drain voltage, right, VSD is changing. In that case, the change in ID will not be very high, because as long as the transistor is in saturation, gate voltage is constant and then you change drain voltage, then you do not have much change in the current. So, that helps it behave like a good current source or an ideal current source, close to ideal current source. If the lambda is very small and the curves in the saturation region are very flat, it becomes all the better, right, it becomes more closer to the ideal current source. If lambda is large, then the curve slope will be large, and then for a given fixed VG also you will get significant change in current even when the transistor is in saturation. So, then the current mirror becomes a bad current mirror. So, first thing is we should not have diode connection for this, and in order to have relatively flatter curves, there are certain options that we have discussed. Lambda is a parameter that is not available to the circuit designer. Lambda is a process parameter. So, a particular fab will give you a device which is having a certain lambda that is not in our hand, but we have seen another parameter that can help us in keeping this curve flatter, that is L. So, if you use larger L, delta L by L goes down, and as a result the curves become flatter and you have a more constant slope in this region. So, that can help us in getting a current source, or that can help the M2 behave closer to an ideal current source. So, later we will discuss some techniques where we can have even better small signal output impedance, even flatter curves without increasing the L. That is the concept of cascade current mirror. Probably we will look into it today if time permits. Another important point that I would like to mention is that two PMOS transistor in an integrated circuit environment, they can be matched to a good extent. So, in the beginning I mentioned that in this device we have a problem. The VD is not very well defined because the parameters of M2 and M1, they are not very well matched. So, we will try to derive what is the relationship for VD in this case. We just did it for the case when you have a ideal current source. But now, if I have this M2, then how do we obtain the expression for VD? That is another question. So, let us do that. But the key point is that M1 and M2 are two different kinds of transistor, PMOS and NMOS. Their parameters, their threshold voltages cannot be very well matched, but in an integrated circuit environment, threshold voltages, even effectively the lambda of two PMOS transistors or two NMOS transistors, they can be pretty well matched. And there comes the concept of layout. How do you do the physical layout of two PMOS transistors that you want to match? Likewise, if you are having a differential amplifier that will be going towards very soon, you need to match the NMOS transistors of the differential pair. So, there we have the concept of layout or the common centroid layout through which we can ensure good matching between two PMOS transistor or two NMOS transistor, but we cannot ensure good matching between NMOS and PMOS transistor. There is another important point we should keep in mind. So, we can have good matching between two NMOS or two PMOS using common centroid layout. I hope this will be covered in a little more detail later in this course, but this is another distinction that we should always have in mind. Now, if I try to as we did it for the earlier case when you have an ideal current source, if I just try to once again see what is the dependency of the drain voltage in case of this non-ideal current source and try to derive the relationship just to confirm what is going to happen if we are having this current mirror based biasing. So, we are trying to make M2 mimic the current source, and then we have the M1 which is the input device. On the top of that we are applying the small signal, we have the DC bias, VG and so on. So, what is the relationship of VD in terms of the device parameters and the DC voltages that we are having? So, here the VGP is fixed because of this reference current source. We just saw how to calculate VGP for a given ID, and likewise the capital VGN is also fixed. So, the DC condition or DC gate voltage of M1 is also fixed. Now, if you want to find out what is the relationship between the VD and the device parameters, I can just equate the currents through NMOS and PMOS. I can write down IDN is equal to IDP, and there once again if I just put in the equation, which is VGSN minus VTN square 1 plus lambda n VDSN. Now, VDS for M1 is just VD, which is equal to 1 upon 2 mu p co x w by L p VSG, which is VDD minus VGP minus mod VTP times 1 plus lambda p times VSD. VSD is once again VDD minus VD. Now, here what are the constant terms? So, this entire first term is a constant term, VGSN is fixed by the DC bias, VT is fixed. So, this entire term is a constant term. Likewise, here VDD is fixed, VGP is fixed, VTP is fixed. This is another constant term. Based on these two constant terms, I need to find out what is the resulting VD. VD is the unknown that we are trying to find out. So, I can represent, I can call this entire term as Kn, I can call this entire term as Kp, and then I can try to solve for Vd. So, Kn times 1 plus lambda n times Vd, that should be equal to Kp times 1 plus lambda p Vdd minus Vd. And then we can take the Kn on the one side, and we have the equation for Vd. So, if I express Vd in terms of these device parameters, I can bring this constant factor down over here, and therefore, Vd becomes lambda n Kn plus lambda p Kp. So, this is the expression for Vd that I obtain in terms of Kp, Kn, lambda n and lambda p. Once again, if you look at what is Kp, Kn, Kp, Kn is Vgsn minus Vtn, likewise Vdd minus Vgp minus mod Vtp. So, here we have the term Vtn, Vtp which can vary. The threshold voltages of NMOS, PMOS, they are not very well defined, their ratios they can vary. As we said, 2 PMOS or 2 NMOS, we can ensure good matching between the Vt of 2 PMOS or 2 NMOS, but not between the Vt of 1 NMOS and 1 PMOS. Therefore, in this case, the ratio Kp upon Kn, we cannot ensure a good matching, stable value. It will depend upon the process parameters and the variations. And on the top of that, we have the lambda n, lambda p directly coming in the denominator. So, this whole thing is scaled by lambda n and lambda p, which is once again highly process dependent. It can vary very significantly from device to device. So, once again, the purpose of doing this analysis is to very clearly understand that Vd is going to be highly sensitive to the process parameters of M1 and M2, on which can vary significantly from device to device, and we do not have much control. We do not have very good way of specifying the ratio. It can have 20 to 30% variations, and as a result the Vd can vary very significantly, because it is strongly dependent upon lambda. So, once again, we cannot ensure that M1 as well as M2 will be in saturation region. Either M1 can enter into triode or M2 can enter into triode. Vd can go very high or it can go very low depending upon all these parameters. Even if you ensure Kp equal to Kn by tuning, then we have the lambda n, lambda p terms left, which are not very controllable. So, the key message here is, whenever we are having active load, we are having this problem of biasing the output node voltage Vd. We do not have much control over the Vd. So, now here if I want to go back and do the small signal analysis, this is regarding the DC analysis. So, we are facing one problem which is related to the appropriate biasing of Vd. So, we will see how to solve it when we come to the differential topology. So, whatever we are doing now, we are building the base for our differential amplifier and op amp analysis. Whatever we are doing here, it will be applicable there. So, here also there are certain mechanisms through which Vd can be fixed. One example is, you can just use a very large resistor over here, Rg. This can help us in establishing an appropriate DC bias for Vg. You can think of it why, because in this case the DC voltage at the gate is going to be same as the DC voltage at the drain, provided you are having AC coupling over here. So, probably we will solve some examples on this, and we will see whether it is possible to establish a good DC bias in this case by using large RG. But in general, here we are trying to just do the analysis which will be carried forward in the analysis of differential amplifier, where establishing a well defined VD is relatively simpler, and we will see how to do that. Now, how do we go to the small signal analysis for the amplifier that we just discussed? Now, once again redrawing the circuit quickly, current mirror branch. Assume that somehow you have been able to fix VD to the required value, and you have the DC. Now, we are talking about the small signal, we are changing the gate voltage, increasing or decreasing by small amount, and as a result we expect the output to reduce or increase by a large amount because of the phenomena we just discussed, right. If you are trying to increase this gate voltage and therefore VGS is increasing, and in order to establish this current, this M2 will try to maintain the same current, because for this VSG is fixed, and therefore the only way M2 can increase the current is by reducing the VD, so that the VSD of M2 goes large. So, if you are trying to increase the VG of M1, this has quadratic dependence. So, ID1 should increase, but for M2 VSG is fixed. So, how does it increase the current? Because if current in M1 increases, current in M2 must also increase. So, the only mechanism for increasing the current in M2 is to reduce VD, and therefore increase the 1 plus lambda VSD term for M2. So, that will enforce VD going down whenever you are increasing the VG. So, that is a basic mechanism how we get gain in this circuit with active load. So, before we do any small signal analysis, we draw that AC model. It is important that we visualize what is happening in the circuit, physically what is happening in the circuit, because this GM and this RO, they are small signal parameters, mathematical models derived from the real device phenomena. So, it is important to understand what is the real device phenomena first, and if this is clear, then other things like the small signal, AC, noise, everything will be relatively more clear. Now, before we draw the small signal model, another important consideration is the signal swing. So, we have discussed in the case of resistive load also what is the maximum and minimum possible drain voltage that I can have over here, that leads to the maximum signal swing that I can have at the output node VD. So, here once again, in order to maintain these M1 and M2 in saturation regions, so that we are having large impedance provided by M2, and also the M1 is in saturation region giving us large GM and large gain, we must make sure that the drain voltage is ensuring saturation region operation for both M1 and M2. So, now towards the lower side, when the VD is going down because of an increasing small VG, the M1 will be in trouble, because the moment VD goes down below VGN by VTN, the M1 will be entering into triode region. So, we can write VD min is going to be equal to VGN, the DC voltage over here, VGN minus VTN. If the VD goes below this, M1 is going to enter into triode region. Here we are ignoring the small VGN in comparison with the capital VGN, the DC condition. That is a fair enough assumption, provided the gain of this stage is pretty large, larger than 10. So, for a given VGN, if the VD goes below VGN minus VTN, M1 is going to enter into triode region. So, this is the minimum VD allowed. Likewise, what is the VD max? So, there again, if your drain voltage is going more and more positive, the PMOS will enter into trouble, right, because in order to make sure that M2 is in saturation, VD must be less than VGP, call it VGP plus mod VTP. That is what we have discussed earlier, yesterday's class. So, VD max is going to be VGP plus mod VTP. The moment VD goes higher than VGP plus mod VTP, once again we are in trouble. So, this is the range of VD max to min. Now, once again, if we have a target that we want to have maximum symmetric swing, and therefore, we want to bias the VD. We want to have VD exactly midway between these two extremes, so that the signal can go up and down by same amount. That is called maximum symmetric swing condition, and under those conditions we would like to have VD equal to VD min plus VD max by 2. That is the ideal, best possible swing for max symmetric swing at the output. So, this is about DC analysis and the swing. Now, let us look at the small signal and try to analyze the small signal model or small signal equivalent circuit for this amplifier. So, one of the strategy to do small signal analysis in this case would be to look at the drain of M2. Below M2, we just have a common source amplifier. M1 is just acting like a common source amplifier. Only thing is, earlier we had RD, we have some resistance over here RD, and that has been replaced by PMOS. So, if we can find out what is the small signal resistance looking into the drain of M2, I can replace M2 with that small signal resistance. In case of RD, remember, it is a passive resistance. There is no difference between the small signal and large signal resistance of a passive resistance. Both small signal as well as large signal are RD, just simply RD. But in case of a MOSFET, definitely we are talking about the small signal resistance, which is not same as the large signal. If you afford to define large signal resistance as capital VDS upon capital ID, that is not the same as the small signal resistance. So, we need to look into the small signal resistance at the drain whenever we are talking about the small signal model or small signal amplification. So, what is the small signal resistance looking into the drain of M2? That we have already seen yesterday. If you are looking into the drain of a PMOS transistor or an NMOS transistor with gate voltage fixed to VGP, VGP is being provided by this reference branch. Remember, the purpose of this diode connected branch is to produce a reference VGP which is applied to the gate of M2. So, this VGP is at a constant DC voltage, there is no signal over here, and therefore, in terms of AC, I can put it at AC ground. And therefore, if you are having the gate of a MOSFET at constant voltage and looking into the drain, you are trying to inject some VT and trying to find out what is the IT, we have seen it is going to be given by RO. So, VT upon IT, the small signal resistance is given by RO. So, you should always have that output characteristics in mind. So, if I am fixing the VD and we are trying to change the VD by a little bit, in this case we are going to get a small change in the current, and the slope of this curve is going to give me the inverse of small signal resistance. So, we should always have this in mind, that the small signal resistance looking into the drain of MOSFET with gate voltage constant is going to be RO. So, I can just replace this by the small signal resistance RO, and in that case I can draw the small signal model for the MOSFET as gate voltage is having small Vg, drain to source we are having GM Vg S, which is just Vg because S is grounded. So, GM Vg. For M1 we are going to have the RO of the M1 coming between the drain and the source of M1, which is ground, and once we have just seen that the small signal resistance of M2 looking into the drain of M2, we can call it R up is just going to be RO2 of M2. So, that is coming between the drain and AC ground, because that is the small signal resistance looking into the drain upward, that is between the drain and the AC ground. So, once again RO2 comes between drain and ground, and therefore, RO1 and RO2 are in parallel. I can write down the small signal gain AV is equal to VD upon VG, that is this entire GM VG is flowing into the parallel combination of RO1 and RO2. Therefore, this becomes minus GM times, or rather GM1 times RO1 parallel RO2. If RO1 and RO2 are equal, which is not going to be the case usually, but just for getting the expression that okay, assuming GM1, GM2 are equal, RO1, RO2 are equal. So, what is the order of the gain? So, we can say it is of the order of GM RO by 2. So, once again very close to the intrinsic value GMRO, only thing is reduced by a factor of half. So, the expression is similar to what we obtain in case of an ideal current source, but by a factor of half, because now you have to account for RO2 also. In case of ideal current source, the small signal resistance looking upward was infinite, therefore, RO2 was infinite, therefore, only minus GMRO1, but now you have RO1 parallel RO2, that is the only difference. So, once again we have seen the DC analysis, we have seen the swing, what is the maximum signal swing allowed at the output, and we are looking into the small signal gain. Now, from the swing and the gain information, I can also figure out what is the maximum input signal swing that can be allowed in this case. So, max Vg, that is the input signal, can be written as max Vd max, that is the maximum output signal, peak to peak output signal that we have just found out, divided by the gain, magnitude of the gain. So, that is in this case GMRO by 2. So, the max output signal we have already seen, maximum value Vg plus mod Vtp, minimum value Vg minus Vtn, and therefore, the maximum input signal that I can have is the max output signal divided by gain of the circuit, mod of the gain of the circuit. And once again, if we want symmetric swing, if we want to exploit that maximum possible signal, then the Vd should be biased close to the midpoint of this two extreme values. So, this is regarding the small signal operation and of the active load common source amplifier. Now, let us talk about the frequency response. How do we deal with the frequency response of this active load common source?